Thank you. My name is Gabor Csaba, and I was invited to make a speech on a short notice. So this is a topic that I have talked about in different forums. It is not. It's a bit off topic from vibrations, but vibration is a part of it because it's about how we make diagnostics of generators, and I will come to what we mean with 100 failure modes. So when we started this development, and I've been working with generators for a little more than 20 years. Started in Västerås at what was ABB when I was hired for the job, and soon became Alstom, and then you have all these different name changes. We started a new company in 2011 that was bought by Fortum in 2017. So today I work for Fortum Turbine and Generator Services. Det är någonting som låter.
Yes, I will try to mute them. In which way? Putin way.
Yeah. So through the years, when I started working with generators and before we were here, that's what we call the past. And I think maybe the nuclear power business is, I don't say that you're still in the past, but because it is a higher value, maybe you have a more effort to have people who are really specialized in equipment and knows the equipment quite well. And in the past, especially when I started working for an OEM, it was like that we. Thank you. So, and in the past, as an OEM, you went to the site and you did your measurements, and then you presented it in a report to the customer. And it could be that you, as a customer, you would get one report for the mechanical work, for the disassembly and reassembly, another report from the test engineers with what they have done. And then if there were any findings, then you would get a third report from engineering. So you have these 3 or 4 reports, and then put them together and make your own assessment of what is the state of my generator or whatever equipment, and then to make your plans from that. And I would say in most industries that's more in the past, that you really had experts to do this analysis and conclusions. What we see today is that, and it's also a bit of a generation shift, that when younger people come in, they have lesser knowledge and they have lesser time to put the knowledge, and maybe they are not just responsible for the generator but for the all electrical equipment at the plant. So we see a bigger need that when we or somebody else provide a service, that you really give them a presentation of the information in such a way that it supports their decision making. So not only tell in the report what you did and how you did it, but also why. What does this mean for my generator or turbine or whatever? Why is this important? Why should I do this repair and so on? And also, as we see, when equipment becomes older, when you deliver new equipment, you have a maintenance plan with 6 to 7 years, every major overhaul, and then other tests in between. But when it becomes older, it's more up to the status of the equipment. So you need to have more tailor-made inspections. And to propose that, you also need to know more about the equipment to propose the inspection program. That's what we see, that there is bigger need to have the presentation of what you do in an easy read way, and also to come with more tailor-made inspection and tests. And so that was the basis for us to start this investigation that we did on the generator. And I guess most of you know a bit about the generator and the main components. And when we look on the generator, we look at in the main components that you have, the rotor, the stator, the exciter, bearings, coolers, and so on, when we make diagnostic of those parts. So okay. So when we started looking into this, we also looked at some statistics that we got, and you can see that the cause for failure on the turbogenerator, so you have a big portion, almost 50%, that comes from the design and choice of material. So those are, you can say, generic issues that are built in with a certain generator, and I come from the ASEA ABB design. That's my heritage. So I know quite well that for certain generators, you know that these things are more or less built in. If you say generic or not, but maybe after 10, 50 years, things starts to fail, but you know some weaknesses in the design. You have some aging, but it's quite a little bit in the generator that you can really say it ages. But the longest time and the most interesting part is actually what comes from operation and environment. So how you operate your generator or turbine, for that sake, and how you maintain it, that has quite a large influence on the causes for failures. And this means also that if you have a fleet of generators that on paper are alike, depending on where you have them, you can get different time to failure. For instance, if you have a generator in a pulp and paper mill where you have a lot of sulfite and the other things, or if it's a clean air of the same generator, different operations. And when you look on the components that fail, more than 50% is on the rotor. And this is for the turbogenerator, the two-pole. If you take similar for four-pole generators, because you operate it at half the speed, you have approximately 1/4 of the centrifugal forces. So at least on the air-cooled fleet where we looked, majority of the failure comes in stators on the four-pole, while on the two-pole it's the majority is on the rotor.
Is it mainly end winding, stator winding?
Yeah, for instance, yeah, stator and winding and core. We have now a generation of where the stator is made from global VPI, where we see quite a lot of failures and partial discharge and so on, because of the VPI process was mainly perhaps not 100%, and also because of all the movement we have. So that's quite.
What is VPI?
Huh?
What is that process?
So you have two different, when you make the. No, if you start when you build, yeah, when you build the stator, you have one process where you make the core in. The core is a number of laminations that you put into either into the frame or you stack them separately, and then you have a system where you have already cured stator bars or semi-cured stator bars, and you insert them and you build the stator by that. That's one way. But what they call the global VPI, that means that you wind the stator bars with a winding that does not contain the epoxy. But after you have built the whole stator, then you put it into vacuum in pressure impregnation tank. So you really need a big tank for that. And then you get the epoxy into the system that glues the stator winding as well as the stator core. So when it's new, everything is well glued together. But then as soon as you start to get starts and stop and heat cycling, you get forces that wants to crack this epoxy. Some suppliers have methods to allow for some relative movement, especially in the bars. But it works up to a certain size. And from a production point of view, it's cheaper to build the stator in that way compared to stack it and then wind it that way. So in certain fleets, you have some certain failures that occur more often. So what is also important to know, and this is typical for the generator, that we talk about generator maintenance and overhauls, but the generator overhauls, about 90% is the diagnostics. There is very little reconditioning that you do, especially if you have a clean environment. You have some gaskets that you change, you do some cleaning. Maybe you need to retighten the stator slot wedges, but it's quite a few normal maintenance that you do. And this also, and the other fact is that the generator usually it just runs until it doesn't. Especially if you have very little monitoring of vibration and temperatures and the other early indicators. If you just run it, it runs and then it fails, and then you wonder, shit, what happened? So therefore, the important thing is to do your diagnostics on the generator and try to see what is coming before it does. So we had some of our really senior experts looking into the air-cooled generator here, and we came up with that there are about 100 failure modes that can occur on an air-cooled generator that can cause an unplanned outage. I think we counted it to 95, and many of them are the same. If you have, for instance, a hydrogen cooled or a hydrogen water cooled, then you need to add some failure modes to that for the hydrogen seeds, for instance, that we don't have in this model. So we made a list of different ways that the rotor and stator and the other parts can fail and cause an unplanned outage.
You have one line in the diametrics.
Yes, yeah, we have that ready.
Yeah, that's good. So the other one.
Yeah.
Points in there.
And the next step was that we looked into the diagnostic methods that we have. So we have the different electrical tests that we do on the rotor, on the stator, and the exciter, where we look for the if there is any short circuits, if there is any weakness in the main insulation, and so on. So that's one portion of the information that we can get. What is also very important is to do the visual inspection with what we call the trained eye. That you have an inspector that has experience and knows what he or she is looking for. That you observe that this is normal, this is not normal. What is this? For instance, in the stator end winding, if you see white powder, okay, you know that comes from vibration. If you see a yellow powder, you know that this comes from partial discharge.
So this white powder was something else.
Yeah. Could be, yeah. So the diagnostics, there are a number of diagnostics tests and visual inspection, and then you gather this with the experience from the personnel. So that comes to fill your matrix that will come later. And then you look at these diagnostics tests, that also you need to relate it to when can we do these tests. And typically for a generator, you have 3 levels. We call them safety check. Is what you usually do once a year when you make some basic electrical testing. You open some hatches and you look into the generator. I know that you do more than that on the nuclear side, but if we look on the smaller generator, basically there's a small level of inspection you do every year. And then from time to time you do something which is a little bit bigger, a limited inspection. And typically you would lift the upper halves of the bearing and inspect if there's any damages on the bearing or if you can see anything that has come from the oil. And you look into, maybe open a bit more, so you take away some of the winding covers and look more into the generator. And then you have the major overhaul, and that's really when you get full access to the generator. And in this example, you have the rotor out here, and you have this. This is a special type for those who recognize, because you have 2 generators and you have 1 steam turbine in between. This is the famous radial steam turbine that you have, where half of the turbine is coupled to 1 generator and the other half coupled to the other generator. So when you remove the turbine and both rotors, you get really good access to inspect the rotor and inspect the stator and to do complete diagnostics. If there are any questions, please just interrupt me. So this is part of the list, but this is the matrix that you talked about, Paul. That if we look on this matrix, you have the 100 lines, which gives all the failure modes that you have. And then you have the diagnostics test that you can do. And we group them in what you can do with the safety check, what you can do on the limited inspection, and what you can do on the major overhaul. And then you see some boxes, some crosses which are filled.
Like Diam?
Hmm?
Is it like Diam?
Yeah, I think it's similar to that. Yeah.
Okay.
Yeah.
Uh-huh.
That this means that a D here means.
But this is only the first sheet in the end.
Yeah.
We have not this solving analysis solving.
No, no.
And the mitigation part.
No.
Yes.
This what this matrix does, that it tells you which failure modes that you can have and how you can find them.
Yeah. That's the same.
But maybe it's something for you to.
It's something to incorporate into the other thing.
Yeah.
Because then, if you have identified something, then comes the next step, what you do with it.
Yeah.
If you have an observation. And what this means that a D in this one, that means that you have detected something that with this maybe it's difficult to see. We have an example on the next page. We can go to the next page. It shows a bit better. So a D means that you have detected something, that it can be 1 or more failure modes, and an I means that it's identified. So for instance,
Question mark. The D question mark.
Yeah, yes. The D question mark, it means that you might be able to see an interturn fault with a visual inspection, but it's quite seldom that if an interturn fault, that means that, for instance, that you have a turn-to-turn insulation in the rotor which is missing. So if you look in the end winding and you can see a big piece of insulation sheet that is dislocated, then you know, okay, this is the interturn fault. But it can also be that you don't see it. So this is a good example, because if you do an electrical test like the impedance measurement or the RSO test, then you can identify that you have the interturn fault. So it's a good example there that you can detect, or actually, usually it's the combination, because usually you start to do the electrical testing and you see that, okay, we have an interturn fault here. And then you do the visual inspection, and if you see it, then it's good, because then you also know what you can do and how you should solve it. But quite often you don't see directly where it is, because it can be inside the rotor slot. So and that's why also usually that's what I say is the combination with the testing that you can do with the visual inspection, that's really the most powerful. And you also see one of the examples of something which you don't detect, because thermal instability of a rotor, that's not something that you see, because these are only standstill tests, but that's something that you see in operation. So these are the tests that you can do at a standstill, and then added to that are the tests that you do in operation. So if we go back, we can do so when you take the complete list with 100 failure modes, then you can count and see how many of those can you find when you do the major overhaul, and how many can you find when you do the limited inspection, and how many can you find in the safety check. And also it's important here that you do everything at the major overhaul. For instance, you have the LCID testing of the core. Sometimes when you as a customer purchase the major overhaul of a generator, you include some of the tests, but not all of them. Then we can also see what does that have as an effect. Because if you do the major overhaul with all the tests, you cover 95% of these failure modes. And the ones that you don't cover, that's the one that you detect during running, like the thermal bend of the rotor, or if there's a crack deep inside the rotor that you cannot detect with ultrasonic, then you see that as an increasing two times speed vibration. And that's why we also say that it's very important when you do take the rotor out, that you really do everything that you can do, because you can find all these potential problems. Don't take the rotor out and don't do everything. And of course, with the nuclear power units, everything becomes more expensive. I can already answer maybe one of the questions. We haven't looked at the inspection with the robotic tool. We haven't looked at that. It's something that we have thought about, but it's not done. But it's of course something that we can do, especially if one is very interested in that. So in the same way, you can do, and you can see that the smaller inspections, the safety check and the limited inspection, they have quite a few number of failure modes that you can find, 25 and 30%. While, as I said, the major overhaul covers 95. What is interesting is when you look on what we call online diagnostics, then you can see that it's not so many that you can identify, but you can detect quite a few. So the number of ones that you can identify plus detect are 55%. And of course, these three are the offline, when the generator and turbine are at standstill. And this is online, so it's also convenient that you can do it whenever you want to do it, when the unit is running. And to give you the example, and this is for the online diagnostics of an air-cooled generator, that you already have vibration sensors installed And normally you have bearing temperatures, winding temperatures, and core temperature. And of course, on the larger generators, you have also something for the cooling water and end winding vibration probes. And by looking at all those online data and analyzing that, you can detect much more than you do with the regular checks. And for the air-cooled generator, we always recommend, when you have a major overhaul, to implement the rotor flux monitoring. And at any stop, when you have an outage, you can implement the see if this link, the partial discharge monitoring. Right. Det är inte samma?
Nej, det blir en del på en annan.
Aha, va?
Skärmen delar på en annan.
Jaha, okej. Jaha. Nu vet jag inte vad som händer. Nu ändras det inte där. Nu ändras det.
Nej,
Vad ut?
Men det är en prestation tillbaka.
Ja?
Funkar det nu? Nu är det tillbaka där.
Ja.
Men vill du visa upp?
Jag skulle visa. Jag behöver. Okay, so later you will have the transcript and then you can see in detail. So one measurement device that we really recommend everybody to install is the rotor flux monitoring, and that is keeping track on if you have shorter turns in the rotor. So if you have a turn, the rotor is, you have quite many winding turns in the rotor, and if you have a short circuit between the turns, if you have one shorter turn, usually it doesn't affect the operation of the unit. But once you get more, then you can start to get vibration and problem to excite the rotor. And especially on the larger units with fewer turns, each turn that is shorted will have a higher current going through the short circuit. You will have an acceleration in that. And so when you take the rotor out, you install, and that's what you see better in the transcript. You install a probe either on the teeth of the core or if you have larger air gap, you install it on one of the slot wedges. It's like this flip up probe, and then you take the signal out of the generator, and with the measuring equipment you can measure if you have the shorter turn and get the trend of that. The other thing is to monitor the partial discharges. Usually it's not a big issue if you have a hydrogen cooled generator. They are less prone to partial discharges. But if you have air cooling, then it's much more interesting and important to have the monitoring for the partial discharges. And you don't only look on the number of discharges you have, but you also look at, you will get some patterns. And you really need to be an expert because you get a pattern of these charges, and from that you can see, is it in the end winding, is it in the slot, and if it's in the slot, is it between the bar and the core, or is it inside the bar? So there is a lot of diagnostics that you can make from these measurements. So those are the two most important we recommend for all generators. And the partial discharge is installed in the terminals. So you can do that whenever the generator is stopped. But of course, if it's a hydrogen cooled, you need to evacuate it from that part from hydrogen. But for the rotor flux monitor, it's easiest to do when the rotor is out. There is a variant that you can install with the rotor in situ, but it's more work to do that. Okay, so now you have done the diagnostics. Then the most important is the report, because that's what remains after the work is done, and what remains for a number of years. So when we do the diagnostic testing of the generator and we find that there is a deviation, we make risk classification, and that's done per component, and then it's aggregated for the generator. And it's like a chain that the strength of the chain is equal to the weakest link. So if there's any component that has a higher risk, then that becomes the risk of the generator. And you will see that in the front page of the report. You see the risk classification, summary of what has been discovered, and then there are always recommendations for what to do about what has been discovered. And basically, the green one is base risk, because any time that you run the unit, there's always a risk that something happens, so there's no zero risk. But if it's a fully functioning component, but you see some deviations, that for instance, the insulation resistance is outside what is normal, but it's not alarming, then you get the yellow light. If you see, you know exactly which failure mode is active, and you know that this is something that will, with time, lead to a forced outage, then you get the red light, the risk level 4. If you see that something is bad, but don't exactly know which failure mode it is, then that's when you get the orange, the number 3. And when we do the diagnostics in this way, we always report before we leave the site, and especially if there's a 3 or a 4, then you as a customer should have the chance to do something about it during the outage and not read it afterwards. And we see that to work in this way, it's really fruitful to have not only what we discovered, but also the recommendations. In that way, that you can divide that in 2 different groups. One which is recommendations that will affect and reduce the risk, and the other one is recommendations that can reduce the consequence. For instance, if you see a stator winding in a bad shape, if you buy a spare winding, you don't reduce the risk that something happens, but you reduce the consequence. You already have the spare winding or whatever spare part needed on stock, ready for a later implementation. As an example. And the way to do work in this way, with the traffic lights and the clear recommendations in how this risk is affected by the recommendation, that gives you as a plant owner a powerful tool to plan your future maintenance and future activities on the generator. Some examples that I put together. One is that I'm talking about the slot wedges, and the main purpose of the slot wedges is to keep the stator winding in place. This is a cross section where you have two bars, and then you have a force from the slot wedge to keep them in place, and this can be radially, but there is also parts to keep them in place laterally. If it comes loose and if you start to have vibrations, then you can have damage to the stator bars due to vibrations, but also due to partial discharges. And that's what you can see on this one, because the partial discharges, they go between the 0 and the slot. And so you can see some lines here. These are the ventilation areas. There you don't have any discharges, but you have discharges here. So when the bar is moving, because to have to have the electrical discharge, you need to have the right distance for the discharge to take place. So if you have vibrations, then at a certain time you will always have the right space to get the arcing here. And usually it's more, for instance, if you have end winding vibration, that end winding vibration goes into the core. Into the slot. So you see more damages here and less damages when you come closer. And this is something that you can discover with partial discharge measurement online. And you can also diagnostic sometimes with offline testing. Online, you get influence from vibration. Offline, you don't get that. So sometimes you don't see anything offline, but you only see it online when it's vibrating. And usually when you do a visual inspection, you can see this white powder. So the combination of the electrical testing and to be able to see this, that's really something which is fruitful in diagnostics. And this would be also something that you probably would discover with the robotic inspection. But that would be that it's really bad that you start to get see the white stuff. The other example, which is also interesting when we talk about vibration, I talked about shorter turns. So this is a rotor where you have about 30 turns per slot. So in total you have around 200 turns per pole. So it's quite thin copper. And if you get, and therefore if you get the short circuit between one or two or three turns, it doesn't give much, and you need more turns to have a problem. But that's also something that you can detect with vibration, because if you have shorter turns in one pole compared to the other, that pole will run, the pole with the shorter turns will be colder, because you have the same current going all the way. That's something that you could detect during operation. And that's also one interesting testing that one can do, because usually when you have vibration problems in the generator, the first thing you want to, is this a mechanical problem or is it an electrical problem? If you keep the active power constant and you change the reactive power of the generator, then you also change the excitation current and voltage, and then you will see the effect if it's something which is used electrically. That's usually something I recommend if there's a vibration problem and you want to investigate. If you have possibility to keep the active power constant, change the reactive power, then you can see if that influences the vibration of the generator. Then you know it's something that is affected by the excitation. So this is the summary of what I have presented, that I talked about, that we have identified these 100 failure modes and how different type of inspection can find these failure modes. And when we do an inspection of a generator, we do the risk classification in 4 steps. So, and it's the diagnostics testing, the electrical, ultrasonic, and the other testing combination with looking at the generator with a trained eye and to know the history and understand design weaknesses that makes this a powerful tool. And we, at the end, you will get a report with the risk classification and the recommendation on how to mitigate this risk. And we call this generator peace of mind. This is the slogan for this diagnostic. And we did this for generators, and it's possible to do for turbines and other components as well.